In this last lesson, the exponential functions unit, we're going to look at some applications, how we can actually create models, use models, solve models in the real world. And for our purposes, exponential functions are going to take the form y equals b times a to the power of x. B is always our initial value, it's our starting point, and a is our rate of change, okay? How it's changing. Is it doubling? Is it tripling? Is it increasing by a percentage? And it could increase or it could decrease, and we'll have to deal with that when we get to them. And we've talked about exponential models, ones that increase over time. We said those are increasing functions, and they go up to the right. We're going to call those growth. Okay? They're growing over time. I think the purple one here. A function that decreases over time, we call that decay. They're going down to the right. And as we know, these things level off to a horizontal asymptote, and we can maybe figure what that is down the road. Okay, some things we need to talk about. Rate of change. The rate of change sometimes is given as a specific value. Your function is doubling. Okay, that'd be an a value of 2. It's tripling, an a value of 3. It's quadrupling, an a value of 4. Maybe it's cutting in half, halving, a third or a quarter or a fifth. Okay, those would be fractions, obviously. Okay, other times, and most of the time, will be given as a percentage. Okay, in this case, we have to add or subtract that percentage to 1. The reason we do it to 1 is when I multiply things by 1, they stay the same. And it doesn't matter if there's an exponent on here, and 1 to the power 5 is still 1, it would still stay the same. So if I want things to grow or decay, I need to make it slightly bigger or slightly less than 1. So if I want something to grow by 1%, I take my 1 and I add my percent. Now we don't usually like working with percent and decimals at the same time, so we turn our percent, let's say it was 1%, into a decimal, so divided by 100, 0.01, and I would add that bit to my function to make a new growth factor. Okay, if that would be a growing example. If I wanted to decay by 1%, I'd do 1 minus that decimal. Okay, so it's all in relation to 1 when we're dealing with percents, and you have to actually read the question in terms of is it growing or is it decaying and by how much. Okay, so we look at the first example here. I want to look at the initial value and the rate of change for these various exponential functions. So the initial value is easy to recognize. Okay, it's the number out front, your b value. So initial value, just go IV, would be 300. My rate of change, okay, that's coming from this part over here. The a value is in relation to 1. So how much different is this from 1? Well, if I take 1.05 and I subtract 1, I end up with 0.05. So as a percentage, times that by 100, this would be a rate of change of 5%. Because it's bigger than 1, it'd be 5% growth. Okay? Now, you don't have to show all the math. You can look at it and say, oh, it's 5% bigger. Okay, 5% growth. Look at the next one. Our initial value, that would be 10,000. Our rate of change, the difference from 1, I got 0.62. I subtract 1, I end up with negative 0.38. What does that tell me? Well, 0.38 is 38%, and because it's a negative, this would be decay. Okay. 38% decay rate. This one's getting smaller over time. It's less than 1. Okay, if we try the last one here, our initial value, starting at 1/2. My rate of change, okay, 3 minus 1 gives me 2. As a percent, that's 200%. It's a positive, so it's growth. The other way you could do this one is you could say that this is tripling. It's a factor of 3. And I don't care if you use the word tripling or if you use 200% growth, they mean the same thing. Okay, when they're whole numbers, you can use that double, triple, quadruple, whatever it happens to be. Okay, so that's how we recognize things. Our objective today is going to be building these things. So let's take a look at the first one. The population increase on a Pacific island since 1970 can be modeled by this equation, where T is the years since 1970. Part A. I want to use technology and draw a graph. So we're going to go back to that Desmos website. Okay, hopefully you have it on your phone, your iPad, whatever you're working with, your computer. Okay, I'm going to take a look at mine here. Okay, we're going to want to enter this equation in here. So I'm going to try and move this a little bit once it loads. Start graphing. Okay, where is my equation here? It's over. So P, well, we know we can't use P, we're going to use Y. So Y equals 2,500, and then brackets, 1.2 bracket to the power of. Now, for decimals to work properly, whenever you have exponents that have more than one piece, you have to put the exponent in brackets. So I'm going to put a bracket in and say 0.3 with an x attached to it. And then close my bracket. That way it knows it wants that whole thing to be our exponent. Hey, now you notice I can't really see anything right now. It makes sense, right? My initial value is 2,500, so I'm going to have to zoom this graph out a little bit. Okay, zoom out, zoom out, zoom out, zoom out. And there's my graph. It's starting to come into play here. And move it down a little bit so I can see some things. And there's my graph. Okay, so we made some technology. Part B, what is the growth rate? Well, I don't need my graphing calculator to do that or my technology. My growth rate is my difference from 1, my rate of change. So 1.2 minus 1 gives me 0.2 or 20% growth. Okay, part C, what was the population in 1970? Well, the equation said that this is time in years since 1970. So in 1970, that was my initial value, my starting point. The population was 2,500 people. Okay, part D, use the equation to determine the population in 2010. Okay, so D, my population was 2,500 times 1.2 to the power of 0.3 times T. Now T is the years since 1970. So how many years is it from 1970 to 210? I think that's 40 years. So my T is 40. Okay, so if I'm going to use my calculator, and I can use my technology calculator or my regular calculator, the exponent I actually want would be 12, right? If I'm using the technology, I'd be writing in, okay, what happens down here when X is 40 years. Okay, there's my graph. Now it's kind of hard to read this graph here at this point. Okay, so I need to figure out where 40 is. Drag this up or down. And I want to know where they touch each other. You know, it's a little tricky to tell on here. May not be the best way. So maybe I'll go back to my regular calculator and punch in this equation, right? It's hard to tell from that graphing one because they're so close to each other. It's one of the not so good things about technology. But if I punch that in, my calculator, I get 22,290. Okay. When we're using technology, solving for values isn't the best option for x's. Y is yes, x is not so much. All right, part E. When was the population greater than 34,000 for the first time? So I want to know, when did I hit 34,000? I want to solve the equation 2,500 negative, not negative, sorry, 0.3 t. I want to know when this is true. Now yesterday we did exponential equations. We said we make the bases equal. I can't really do that here because these are decimal bases. This is why the technology is helpful for us. Okay, it's not solving for x, it's solving for y. Okay, I want to know when y equals 34,000. So I'm going to put in equation 2, y equals 34,000. And then I'm going to figure that out. So on my graph here, I got to go all the way up to 34,000. Oh, there it is. My line's hit. I'm trying to find that point. We'll touch it. Our gray dot says 47.719. Okay, so time equals 47.719. When is that? What year is that? Remember, 1970 was our starting point. So if I took 1970 and I added 47.7 years, I'd get the year 2017. Okay, and so we can solve that problem. Okay, you guys are going to try the next one here. I'm going to try and set up an equation and try and solve some parts and pieces of it. And the area of land covered by rainforest is declining. There are currently 1.5 million hectares of rainforest. That's right, an exponential function that can model this. So I'm going to use R for rainforest. What am I starting at? 1.5 million. Now I could write in all the zeros. I'm just going to use the word million in here because it makes my life easier. Okay. It's declining. So I'm starting at 1, and I want to subtract, because I'm declining, 3.5%. So 3.5 divided by 100 would be 0.035. There's my growth, or my decay factor, need an exponent. And I can use this equation the way it is, or I can make it slightly easier if I actually add the part in the bracket or subtract the part in the bracket. I end with 0.965x. There's my best equation. Okay. Determine the land that's covered in 10 years' time. So 1.5 times 0.965 to the 10. And I could use technology, but as I said, you'd be trying to find the x, and it's not really good. It's kind of messy. It'd be easier to just punch this into your calculator. And if we do that, we end up with 1.05. And remember, this is million. I didn't want to write all those zeros in, and that's hectares. Done. All right, part C. Number of years it will take for the forest to decline to 0.5 million. So I want to know when the rainforest is 0.5. Based on this equation, I need to solve for x. Okay, here's where technology comes in handy. Let's solve this value. So we need to make a new question, right? Let's get rid of these old graphs. We're going to make a new equation, y equals, what's our equation here? 1.5 bracket 0.965 bracket to the power of, I want it to be an x. Okay, I can just use just the x this time because there's not parts and pieces up there, just x. I get this lovely equation. Okay, I'm going to zoom back out again, back to my, actually back to home, so it looks like normal. Okay, I'll zoom in if I need to, and just to make it look exponential. Oh, wrong way. Zoom out, make it look exponential. Okay, I want to know when this population hits 0.5, y equals 0.5. Okay, I can't really see that, right? It's pretty small, so I'm going to zoom back in. Playing with the zoom a little bit isn't, oh, wrong way. Playing with the zoom isn't the worst thing in the world. You can zoom in, zoom out. I want to know where these two things hit. They aren't hitting yet, not hitting yet. Move over a little bit. Okay, let's touch that line. Gray point, 30.836. X equals 30.836. So it's going to take 30 years for this rainforest to decline from 1.5 million hectares to 0.5 million hectares. Okay, hey, we got one more and then we're done. A strain of bacteria doubles every hour. Suppose there were 2,000 bacteria to start. Write an equation to represent this. Okay, so I'm going to use B for bacteria. I'm starting at 2,000. It's doubling, so I can just put the number 2 in there. I don't have to worry about this percentage idea to the power of x. Done. Okay, part B. How many bacteria after 6 hours? Okay, 2,000 times 2 to the power of 6. I can put all that in my calculator all at one time. I end up with 128,000 bacteria. And part 2. What happens after 10 years, or 10 hours? So obviously there's going to be a whole lot more, right? 2,000 times 2 to the 10. Okay, punch that in my calculator. I end up with 2,048,000. And I should put units in here. Bacteria. Bacteria. Okay. Part C. How long would it take for there to be 20,000? So I want it to be 20,000. I'm starting at 2,000. I want to know the x, the unknown exponent. Technology comes in handy. Make some new equations here. We'll get rid of that one. All right, first equation. Y equals 2,000 times 2 to the power of x. Can't really see it. That's okay. We'll fix that in a second. Hey, my second equation. Y equals 20,000. I want to know when I hit 20,000. I definitely can't see that on my graph, right? So I need to either zoom out or get way up there really fast. I'm going to zoom out. I think it'll be faster. Okay, I want to be able to see 20,000. Okay, keep on zooming out here. Zoom, 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 zoom. There, we can see up to 4,000. There we go. Oh, went too far. Right there. There's my gray dot. You know, if I want to actually see where they are a little bit, I might have to zoom in just a little bit here. I want to touch it from my gray dot. I'll get rid of that one there. I want to touch my gray dot right there, 3.322, and there's my answer. Okay, and that takes us to the end of exponential functions.